Nope, this is what I want you to do. Write as an equation of x and y, sketch it, and indicate the direction of the curve. Yeah, you should know what that is, and especially with the equation of x and y, then you should be able to, having that equation, make the sketch. Sure. Well, you didn't start talking, so I guess it's a quiz. Be quiet, it's a quiz.
Take 2 points. I would assume that if both of them were positive, though, wouldn't both be going clockwise? Yes. Since one's negative, wouldn't one be counterclockwise?
It can also be negative because you're squaring it, so it's going to be possible.
Yeah, but not with the t.
So by that logic, x equals cosine t and y equals sine t would go clockwise.
I buy that logic, yes, but I'm totally wrong, I'm sure.
Well, which way does it go? X equals cosine t and y equals sine t. Which way does that go?
Look, I'm assuming counterclockwise because you want to get me to an answer that isn't what I would come up with, right?
No, I want you to think about some mathematics.
So
Not this isn't psychology.
All right. We have x sine t or cosine t. That means that f y 0, y would equal 0. So maybe I am wrong because I have cosine equals pi. It is pi. This one is pi. Oh mean the one that.
Okay, so
I have counterclockwise still. Although I think the negative still matters. No, because it changes the value that you get. Like instead of rotating it this way, it'll rotate that way. So if x, okay, that's kind of interesting. So if x is sine and 1 is negative, it'll be counterclockwise. But if x is cosine and 1 is negative, it'll be clockwise. Both are negative.
okay. Hector's not here. Who's this Alec Hutchings? Hutchings is up there. How'd it go? Yeah, this. The weekend. How'd the weekend go?
You're asking that.
How did you do it? Okay. So sine t is x over 3. Good. Negative y over 2 equals cosine t. Okay. Okay. And why can't we just square those and add them together? Why can we do that? Right, because our identity, right? Our identity says that sine squared, we always, no matter what t is, sine squared t plus cosine squared t will always equal 1. Well, that's sine, so we can square it. That's cosine, so we can square it and get 1. And so, x, so we get x squared, what? And can we make a rough sketch of that? I'll let you off the hook here. How about, where's Andrea? What was your sketch like? Did you get it? Yeah. Did you give me some key points? Okay. Okay, and then 0, 2? Okay. And so then the question is, can we get the direction of the curve without plotting points? Without plotting points, can we get the direction of the curve? That's the mathematician's way. So without just putting in values of t and seeing where the points go, we talked about a way to do that. John? Okay. Okay. Okay, so dx dt is 3 cosine t. Okay. Okay, but so it's positive when is this positive? Because this is positive and negative. Well, this isn't always positive. This is also negative, right? It's a cosine. So you just said it's positive. So, but no, it's half the time it's positive and half the time it's negative. So what? Okay, from 0 to pi over 2. Okay. Okay. Well, we're trying to make the connection between. You said this was positive, and therefore it was going a certain way. So we're gonna. What's the connection between? When is it positive, and why is it telling you it's going to go a certain way? Like the direction of the curve. Okay. Yeah, there's definitely more to it than that because okay. Ben, did you want to chime in?
I don't know. Like if you're at the top of the circle and you go to the right, you're going clockwise. If you're at the bottom of the circle, you go to the right, you're going counterclockwise.
Right.
So you have to know more than just.
Exactly. So if we were here and this derivative was positive, x would be increasing like this, and that would be clockwise. If we were here and the dx dt was positive, we would be down here and we'd be going counterclockwise. You see? So we need to put some things together here and to determine this. Anyone do it?
So would you need the y position at 0?
The y position at 0. At t equals 0?
At t equals 0, yeah, because that would answer that question, would it not?
Okay, so at t equals 0, x is what? X is 0. So yeah, so we don't know if we're here or here. So now we're evaluating this at 0. And when we do that, we get 3, which is greater than 0, but we don't know where we are, right? We don't at t equals 0, we don't know if we're up here, down here, or up here. So how can we find that out? Right. Y equals -2. So we're actually here. At t equals 0, we're at the bottom. And so that's 0, -2. And we got what? Our derivative dx dt was positive. Conclusion? Counterclockwise, because x is increasing. As t increases, x increases, we're going counterclockwise. What now?
Like you have the ordered pair 0, -2.
Uh-huh.
Is there a way to write like a ordered triplet with time?
You could write an ordered triplet, but we're still going to graph it in the xy plane. Yeah. So yeah, if you wanted to specify that your ordered triplet means t x y, that's perfectly fine. You just have to communicate that to whoever's reading your work. But we're still gonna graph in the xy plane, so that's why I usually just keep it as xy.
If you were to graph t in a third dimension, would that look like a spring?
Yeah. So it's a little strange, and it's never really done. But you could have t line axis like this, and then for any given value of t, you'd have like a plane perpendicular to that axis. And you'd have the one point in that plane corresponding to that t value. And so then as t increased, you'd have this string of points that kind of would go around, spiral around this t axis. But I've never ever seen that done. But yeah, that's what it would be like if you did that. Yeah, but I've never seen that. Usually, so these parametric equations, parametric functions, we're going to plot those in the xy plane. Yeah. That's the point you got. Okay, there's two different things. X is increasing. X is increasing because dx dt is 3. And x increasing means going to the right. That's the direction of increasing. So if x is increasing along the bottom here, we must be going in the counterclockwise direction. Yeah. Are we good? Okay, so let's look at a new example. Any other questions on this? So, direction of the curve is counterclockwise. So let's look at this example here. So this is, I showed you this one on the first day of parametric equations. This is x equals t cubed minus 3t squared plus 1. And y is this quartic, negative 2t to the 4th plus 3t squared minus t plus 4. So this is a parametric function based on individual polynomials for x and y. And here's some questions I want you to answer. So I want you to find the coordinates of the point. So for time's sake, let's just do for t equals 1. So just part B, for 1 and 2. So 1 part B, find the coordinates of the point when t equals 1. 2b, predict if dx dt and dy dt is positive, negative, or 0 when t equals 1. Estimate the value of dy dx when t equals 1. And then predict if the second derivative, that would be with respect to x, is positive, negative, or 0 for t equals 1. So I want to show you the direction of increasing t here for the point. I think. No, it's not there. You can get to work even though I'm working on this, but there we go. So this is showing t increasing from -2 to +2 and the points you would get. Slow that down a bit. So if you were plotting out the points one at a time for a continually varying value of t, this is how the direction would be. Okay. You're only doing 1b and 2b, just for t equals 1. Okay. I'll just take away a. All right. Number 1 is the only problem where you're actually doing any computation. Okay. The rest, you're not doing any computing after number 1. You're just reasoning, predicting and reasoning. No. Estimating the value of dy dx. Get a partner and talk. Okay, let's see how we did. You should have gotten a point. Okay, so you should have gotten the point -1,4. And now I'm highlighting that. I've stopped the animation and I've highlighted that point for t equals 1 at -1,4. And so what about dx dt? What would you say for dx dt? Just positive, negative, or 0? Ryan, what'd you say?
It would be negative because as the t value is increasing.
Okay. At this point, right, if the curve is going that way, then for an increase in t, he's saying that x decreases. So dx dt is negative. Andrea likes it. Corey likes it. Yeah, right. So if you're going, sorry, this way, right? So if t increases, x is going to decrease. Dx dt is negative. What about dy dt? You okay?
Yeah, I just saw t equals 1, -1,4, so that's what I was going to ask.
You calculated that though, right?
Yeah.
Okay. So Zach, how about dy dt?
It's also negative.
Because?
Because it's going in the downward direction.
Right. So as t increases, it's going left. X is increasing, but it's also going down. Y is decreasing also, so they're both negative. All right. What about dy dx? What about dy dx? Where's Zhao? Zhao's in. Not here. How about Adrian? What do you think about dy dx? We actually want to predict a value here. We want to estimate the value of dy dx. With respect to x, derivative change, yeah, rate of change of y with respect to x. So, did you have a prediction for that? Okay. Anyone have a prediction for dy dx at t equals 1? What's that?
It's going to be positive. I'd say actually, I would say 1.
Okay.
But
Positive 1.
But I went further because I calculated what the what dx over dt would be and what dy over dt would be.
Right.
And then I divided the two, and then that would
There was okay, so that would definitely get a good estimate, but there was no computing or calculations. I wanted just to get it by estimating. So you think +1?
That's what I would estimate for sure.
Okay. And was that before you did the calculations?
Let's say so, yeah.
What do we think?
How I would do the calculations.
What do we think? So is it +1? Or did he make a math error in his algebra? But it's going this way, right? So is it -1? Why not? You're shaking your head. Oh, come on. You were confidently shaking your head that it shouldn't be -1. Why not? Oh. What's that? Okay, so you were thinking that since dx dt is negative and dy dt is negative, that it would make a positive for dy dx. Okay, that's one way to reason it. What about just looking at this? Yeah, so actually, so t is not this. The idea of the direction of the curve really doesn't matter when you're talking about dy dx. It's just if you were to increase x a little bit, what would y do? Yeah, it's also going to increase, right? So this is upward to the right is our positive rate of change, and what's about 1, right? So it's like it looks like maybe about the same amount of increase in y as an increase in x if you were in that vicinity right there. And so then, yes, if you take we can get that by taking the rate of change of y with respect to t. Yeah, because so what do we have? We don't have y as a function of x, so we can't just do a straightforward derivative, right? We can't solve this for t and plug in and get a y. So no, we do not have that, and it's would be nearly impossible to get. Okay, so that's why we have to express this parametrically. And so if we want dy dx, then we're going to need to we have dy dt and dx dt, and we're going to use those to get dy dx instead of taking the derivative of a conventional function. And so when you do that, so what's dy dt? So you can, if you do the math, you will indeed get 1. So you get 3t squared minus 6t over. Okay. And now we're going to plug what? We're going to plug 1 into that. And we get -3 over.
Does that mean that when we had that circle, it was just like the derivative was just like a tangent? Dy dx was some sort of tangent?
It's the slope of the tangent line, right? Just like it always has been. So it's still in the xy plane. It's still the slope of the tangent line, or the rate of change of y with respect to x.
I just mean if you would get like if you had cosine and sine, you get negative sine over cosine, which would be tangent.
Oh, I see. You're saying it's the tangent function.
Yeah.
I suppose, yeah. If you had the right combination of sine, cosine, or negative, yeah, then you would get sine over cosine. You would get tangent. Yeah. Okay. So what about the second derivative? So what about this one, which is what? What would we predict for that? So remember from your Calc 1. What's going on there at t equals 1 that we could predict this? Okay, so are you looking at imagining x increasing?
Yeah, I'm imagining for each change in x, what the change in y would be.
Okay. Changes in y are.
The same change in x, y over time changes more.
So for the same change in x, you get increasing changes in y? Or decreasing changes in y? Okay, talk about one thing at a time. Don't use the word it, okay? We've got too many things going on here. So what's increasing and what's decreasing? Okay, so what are the y values are doing what through here? Y values are What are the y values doing through here? Just the y values. Increasing, right? Y values are increasing. And what about changes in y? Decreasing, right? So that what? The first derivative is positive and decreasing. Okay? The first derivative is positive. Why? Because y is increasing, but those changes in y are getting smaller. So that first derivative is decreasing. So if the first derivative is decreasing, the second derivative is negative. If the function is decreasing, its derivative is negative. So we've got that the second derivative right around that vicinity of 1 is negative because the first derivative is decreasing. I'm showing that with these changes in y, right? These changes in y. For the same change in x, these changes in y are getting smaller, meaning that the derivative is decreasing, and so then the second derivative would be negative. And that's someone's a concave down, right? So this graph is turning down. It's bending down because the rate is decreasing. The rate of change is decreasing, and so that second derivative would be less than 0. So how would we calculate the second derivative? We've got the first derivative, but again, it's in terms of t, not in terms of x, it's in terms of t. So how are we going to calculate that second derivative? We can do the same thing we did before. We can take our dy dx. It's the derivative of that, right? But we have it in terms of t, so we'll take the derivative of the first derivative with respect to t. But then what? We want it with respect to x, right? So then, just like we did before, take the derivative of y with respect to t divided by derivative of x with respect to t. And then what will we have? We'll have the derivative of the first derivative with respect to x. Okay, so what will taking the derivative of this with respect to t entail? How are we going to take the derivative of that with respect to t? Oh boy, quotient rule, guys, quotient rule, right? Quotient rule on that over dx dt, which is the same thing as it was before. Negative 8t cubed plus 6t minus 1. So we're not going to take time to do that because we got one more thing to do. But so that's just kind of messy, right? It's just messy, a lot of algebra. So to get the second derivative, we're going to take the derivative of the first derivative with respect to t. In this case, we have a quotient, so we need to do the quotient rule. That's our dy dx dt. But then we want it with respect to x, so we're going to divide by dx dt. Well, we already found that, so we can just write it down again. There's dx dt. And then we could do all that stuff, and then if we plugged in 1, we'd expect that the value of that whole thing to be what? Less than 0, right? Negative, right? So if we plugged in 1 to that quotient rule divided by dx dt, we'd expect to get negative because we see the rate of change is decreasing. Rate of change is decreasing. Okay, I want to know where. So what does this look like? An anteater or an aardvark, or what is this thing? I don't know. An alien, a wave? Okay. So if the wave was moving towards a wall, what point of the wave would hit the wall first? If this wave was moving towards a wall, just exactly as it looks, what point on the wave would hit the wall first? Oh, well, you're just guessing though. But we want to be mathematical. What if this didn't end up somewhere close to integer values, right? Mathematically, how could we determine where's that thing going to hit a wall, a vertical wall first? What point? Okay, yeah, they're both saying, right, so we want to find the maximum value of x. How are we going to find the maximum value of x? And a max value of x would correspond to what kind of shape or geometric thing happening? Yeah, it would be like where it would go. It would be going vertically, right? Because the max value of x is where when your x changes, when t changes, x doesn't change, right? So how am I going to get the vertical tangent or the max value of x? What equals to 0? Right, I'm going to set dx dt equal to 0. And so I'm going to get 3t, t minus 2. So at t equals 0 and 2, what do I have? I have the vertical tangent. Which one is this one? So t equals 0 gives me this point 1, 4. So that's the one you guys were saying. So t equals 0 is the point 1, 4. So that was the answer to the question, but what's going on here? Why is there another t value that gives a derivative dx dt of 0? Yeah, there's another so you wouldn't know unless we zoomed out here, but there is another place here where it heads vertically, and it wasn't in the view before. So here at t equals 2, you got another place. So what this is like a leftmost point, right? Like the leftmost point or a rightmost point is where you have a vertical tangent, and it's where your dx dt is going to equal to 0. If you want that point, then you just plug in t equals 2, and you can get the coordinates of that point as well. Because we just found it. Because we got t equals 2 from the dx dt being 0. And it has to be a vertical tangent. Does that make sense? So I got the 2 first. I got the t equals 2 first. And then I came to the graph and said, oh, look, it's right here where it's heading vertically. So the 2 came first, and I was looking for the point second. So it's not the other way around. Okay, so